Hello everyone and welcome to Control Theory and Electrical Engineering tutorials. In this tutorial, we explain how to derive a transfer function of an active low-pass filter that consists of an amplifier, two resistors, and this capacitor over here. So let's immediately start. First of all, let's explain what is a transfer function of this circuit. Namely, observe this input voltage VI and observe this output voltage VO. Let the Laplace transforms of VI and VO be denoted as follows. If in time domain we have VI, its Laplace transform will be denoted as capital VI of S. Similarly, for the time domain signal, that is for the output voltage VO, its Laplace transform is denoted by VO of S. Here we are using the classical notation, that is, the Laplace transforms are denoted by capital letters and time domain signals are denoted by lowercase letters. The transfer function of this circuit, denoted by W of S, is a ratio of the Laplace transforms of the output voltage and the Laplace transform of the input voltage. And as you will see later on in this video tutorial, this transfer function represents a transfer function of a low-pass filter. Okay, let's start with derivations. First of all, let's denote the currents in the time domain. Over here, this current will be denoted as I1. Then the current through this branch will be denoted by I2. And this current over here will be denoted by I3. Let's now express these currents. Let us denote the potential of this point as V minus. That is, this is the voltage potential of this point with respect to ground. From these two terminals of our resistor, we have that I1 is equal to VI minus V minus divided by R1. This is the first expression. Let's now express I2. I2 is equal to, over here we need to invoke a differential equation describing dynamics of the capacitor. Consequently, we will have C, the voltage drop across the terminals, and this should be the first derivative of the voltage drop with respect to time. So we will have d over dt, and let's see what is being differentiated. We are actually differentiating the difference in potentials between this point and this point over here. Obviously, the potential of this point is equal to the potential of this point, so we have VI over here, or actually not VI, we have V minus. And then over here, the potential of this point is equal to the potential of this point, and consequently we have minus VO. And that's it. This is the expression for the current I2. Finally, let's find the current I3. This is relatively easy. I3 is equal to, let's see, in the denominator we have the resistance R2, and in the numerator we have the difference of potentials. That is, we have V minus minus VO, and that's it. Let us further analyze this circuit. The potential or the voltage of this non-inverting input is 0. This is because this non-inverting input is grounded. From the basic theory of ideal operational amplifier, we know that the potentials on the inverting and non-inverting inputs are approximately equal. Consequently, we can safely assume that VI is approximately 0. And if we substitute this expression in these three equations, we obtain that I1 becomes VI over R1. Then we have that I2 becomes, since V minus is 0, then we have the following. We have minus C dVO over dt, and finally I3 becomes minus VO over R2. Next, we can sum the currents entering and exiting this node, and from this equation we have that I1 is equal to I2 plus I3, and now if we substitute the values inside of this equation, we obtain the following. We obtain from here that I1, which is VI over R1, is equal to, let's see, what do we have on the right hand side? We have minus C dVO, let me nicely write it down, over dt minus VO over R2. And that's it. This is the differential equation describing the dynamics of this circuit. And this differential equation will be the starting point for the development of our transfer function. Here's our equation once again. This is the differential equation describing the dynamics of this circuit, and let's apply the Laplace transform to this equation under the assumption that the initial conditions are equal to 0. So we have the following. Applying the Laplace transform to VI, we have the following. We have Laplace transform of VI over R1 is equal to Laplace transform on the right hand side. Since the Laplace transform operator is a linear operator, we can substitute, or actually we can separate Laplace transform. So we have minus Laplace transform of this term over here. Let's write it down nicely. And then we have minus Laplace transform of this term over here. Now, let's analyze what is written over here. R1 is a constant and it gets out of the Laplace transform operator. So we can write 1 over R1, and the Laplace transform of VI is simply VI of S. Then let's see what do we have on the right hand side. Similarly, C is constant. We have minus C, and then we have the Laplace transform of the first derivative of VO with respect to time. Since the initial conditions are equal to 0, this becomes S multiplying VO of S. And then finally we are left with this term. Again, 1 over R2 is a constant, and we have VO of S. And that's it. Now we're almost done. Let's now manipulate and let's now write this equation nicer. On the left hand side we have 1 over R1 VI of S, and on the right hand side we will have minus VO of S multiplying the following, multiplying CS, and then we will have plus 1 over R2. This right hand side can be written like this. We can write it like this. We can write minus the term over here, 1 over R2 can go out, so we'll have minus VO over S over R2, and in parentheses we are left with 1 plus R2 CS, and that's it. And now we are almost ready to give the transfer function. Here is the last equation once again, and from here we can obtain the transfer function. Namely, W of S from this equation is equal to the ratio of VO of S over VI of S. Let's nicely write it down. And let's see what do we have on the right hand side. Okay, so VI goes on the left hand side, R2 goes on the right hand side, as well as this term and a minus sign. So we have minus, let's see, R2 over R1, and then over here we have multiplying 1 over this term over here, 1 plus R2 CS, and that's it. This is the transfer function of our low pass filter, and we can leave it as it is. Let's analyze this transfer function. First of all, observe the following. The gain, or the DC gain of this transfer function, depends on ratio of R2 and R1. That is, by properly selecting R2 and R1, we can tune the gain of this system, or better to say, a DC gain, or a steady state gain. Now, notice over here this term. This term is actually a low-pass filter. The low-pass filter dynamics depends on R2 and C. That is, the break frequency, as we will see in the future video tutorial, depends on R2 and C. And notice this minus over here. What's the purpose of this minus? Well, this minus will introduce a phase shift. It will introduce us a pi phase shift initially. That is, for low frequencies, we will have the shift of pi, as you will see in our future video tutorials. Okay, that's all for today, and thanks for watching, and see you in the next video tutorial.